Okay, so good morning, everybody. Quickly, we shall be rounding up our discussion, our introductory discussion on stochastic processes first. Okay, now all along we've discussed several things that are very important in stochastic process, just to give us a foundation to what comes next. Now, in today's class, I want us to round up every discussion by trying to tighten every loose end in this course. That is the introductory aspect of this course. So let's start with continuing the paragraph we stopped at in my last class with you people. So in my last class, we were still looking at classification of stochastic processes, right? Where we said stochastic processes could be classified by means of their index set or by means of what? Their state space, right? And we were in the state space classification. So please, paragraph now, everybody. Paragraph. Let's say if the values of the state space of a stochastic process, if the values of the state space of a stochastic process are points in a Cartesian plane or Euclidean space, then we call such a stochastic process, an n-dimensional vector process, or we call it simply an n-vector process. Okay? Now, if you remember, we had said that your values in the state space can be drawn from where? They can be drawn from the natural number system, right? And they can be drawn from the integer number system. And when they are drawn from the integer number system, what would it amount to? It would amount to what we call a discrete state space. Okay? But if your values in the state space are drawn from the real line generally, not necessarily a subset of the real line such as the natural number system or the integer number system, then such a state space can be called what? A continuous state space. What if the points in the space or the values in the state space are points in the Cartesian plane or the Euclidean plane, a higher dimensional plane or higher plane or hyperplane rather? Then we call such a stochastic process what? Is either you call it an n-dimensional vector process, or you call it what? An n-vector process. Is it clear? Are you listening? Yes. So that is one end I wanted us to close up on. So in a nutshell, please take a look at this. So this is what, you don't necessarily have to write this because it's part of all the explanations we've been taking. And I told you in my class previously that you should please pardon me if I use the wrong terminologies, okay? Just in case I may have used the wrong terminologies, I told you in the last class to pardon me. Now, we were saying that stochastic processes can be classified, and stochastic processes can be what? Categorized. Okay? So I may have used these languages interchangeably. Okay? But please let us correct ourselves with making our statements very clear. When we say a stochastic process is to be classified, it means you are using certain considerations. Basically, the considerations could be the stochastic process. Are we coming from the angle of its index set, or the stochastic process, are we coming from the angle of its what? State space, or are we coming from the angle of what? Dependency of each of what? The random variables in that stochastic process. Now, when you use any of these considerations to define or describe a stochastic process, you are classifying a stochastic process. Do you understand me? So classifying a stochastic process comes under these three categories. Now, when we say you are categorizing a stochastic process, it means we are assuming that we expect you to use the mathematical property of that stochastic process. And it is based on that you can now start having different types of stochastic processes like random walk. You can have martingales, you can have renewal processes, you can have branching processes, you could have a Poisson process, you could have the Gaussian process. There are so many of them. What differentiates the Gaussian process from a martingale, or what differentiates a martingale from a random walk, is the mathematical process underlying that stochastic process. Is it clear? The mathematical properties underlying that stochastic process. All of them are stochastic processes, but the mathematical properties of each of them vary. Is it clear? So when you classify by mathematical property, you will be doing what? You are categorizing the stochastic process. Is it clear? So please, let's now go into definitions. Let's go into definitions. Quickly. Definition number one. Definition number one is the index set. So, if you recall, we had said let T be a mathematical set. Let T be a mathematical set such that there exists small t's that are members of T, and small t can be okay, let T be a mathematical set such that there exists what? Small t being members of what? T, right? Such that for all t's, for all small t's being member of T, there exists an x t variable that is a member of what? X of t, for T being member of T. Then T is said to be an index what? Set of the stochastic process. Now I'm going to explain this definition. I'm going to explain this definition clearly. Please, once you finish writing, you could look up. Now, so we are saying that T, capital T or uppercase T, will be used to represent what? A mathematical set. Now, what makes this mathematical set we are calling capital T an index set? It is simply because if from that T you can draw small t's, small t values, in which case you remember we said they are usually interpreted as what? Time in a stochastic process. If we draw small t values from capital T, such that for every small t value that is a member of capital T, there exists what? A stochastic random variable or a random variable xt that is a member of the stochastic what? Process. So it means that if I have xt that is a member of the stochastic process, this being member of t, then it means that if I have x1, if I have xt can take values if it's a real line. That is, if our t is a real line. Let me even put this properly. If our t is a real line, let's even consider particularly a subset of the real line like the natural number system. Let's consider this. -1, -2, -3, and so on. Now, this t here makes xt as a whole to become attached to each of these. So at every point in time, you could have x1, x2, x3. That's why we are saying there exists what? An xt variable from the stochastic process. You remember we said a stochastic process is a what? A collection or a family of what? Random variables. So these xt values are the random variables you have inside what? The stochastic process. This here is a stochastic process, but this here is a random variable in that stochastic process. So if there exists this that would always take a value from what? From t, then it makes t the index set of that what? That stochastic process. Because at every point in time in the stochastic process, xt would t would assume a value uniquely for what? Xt. Is it clear? So let us now move on to the next definition. Now, what we are supposed to make as remark under this is a remark or our remarks we've already made. Now, look at it carefully. If we say that let xt be a mathematical set such that there exists what? T, that is a member of t, such that for all t being member of t, there exists xt, a member of the stochastic process. Then what is happening? We say t is said to be what? An index set. Do you remember that we have said that if these t's being member of xt, look at this. This is just by the way. We have just to show you that we have already said what we needed to say. If your t being member of t are from that is, if this is equal to, if your t is a member of t and t is equal to n, what would you call that stochastic process? It will be a what? A discrete time stochastic process. Even when it is also t is equal to what? I, if I represents our integer number system, it is still what? A discrete time stochastic process. But if t, the t's that are member of t is equal to, that is t that is a member of t is drawn from what do you call it? The real line in general. That's either you're writing it like this or like that. Then it means that what kind of stochastic process would you have? A continuous what? Time stochastic process. It will be a continuous time stochastic process. Is it clear? So there is no need to make that remark under here because we've already made it previously. Is it clear? Next definition, number 2. Number 2, state space. State space. So the state space often denoted as S of a stochastic process. Are the values assumed by each xt of the stochastic process. If I don't want to put this, I hope you know that I could just wipe off this and say assume by each what? Xt of the stochastic process. Is it clear? And if I don't want to put this statement here, I hope you understand what I'm saying. Good. So this xt, look at it, everybody. See, look up, everybody. Now, xt is a variable in the stochastic process. This is not the stochastic process. If you want to make it the stochastic process, then you have to make it what? A collection. Is it clear? A collection of these random variables will make the stochastic process, but without putting these, you are not referring to a stochastic process. Is it clear? You may be referring to a random variable at a specific time in that stochastic process, but not the entire stochastic process. Am I understood? Now, look at it carefully. T here assumes values from what we call an index set, but xt assumes value from what is called what? A state space. So xt could be 1, it could be 2, it could be 0, it could be any value. That is xt as a variable is the one assuming these values. You understand me? So when you refer to the values assumed by xt, which could be x1, x2, x anything, you are referring to the state space of that stochastic process. But when you refer to the values assumed by t, you are referring to what? The index set. Is it clear, everybody? Thank you. So, next definition. Of course, again, I hope you remember that we don't have to make any remark again, because the remarks we would have made here, we've already stated them. You get me? Of saying what will happen if xt, the values assumed by xt, are drawn from what? The natural number system. It will be a discrete space stochastic process. You know, so when xt values are drawn from the integer, the real number system, it will be a real valued state space or a continuous what? State space. You understand me? And if xt, before we started this definition, we said if xt is drawn from what? A Euclidean space or n-dimensional space, then you will call it what? An n-vector space or n-dimensional vector what? Stochastic process, right? So please, we've already made that remark, as such, we proceed. Next is what we call the increment. Increment of a stochastic process. So, by the increment of a stochastic process, we are referring to the change. We are referring to the change in the stochastic process. We are referring to the change in the stochastic process due to a difference in its index values. Huh? So when you change, if in a stochastic process you have x1, x2, x3, are you listening? The difference between x1 and x2 is called an increment, because you have just moved from one space, okay? You have moved in the stochastic process from one index value to another what? Index value. Even if you move from x1 to x3, it is still an increment. You understand me? There's an increment from x1 to x3. There's an increment because you have changed from one index value 1, t equals 1, to another index value t equals what? 3. Is it clear? So whenever there is a change in the stochastic process as a result of a difference coming from what? The index values, we call that change an increment. Is it clear? Please take note of those definitions. Then definition number 4. sample function or realization. Sample function or what? Realization. So a sample function or realization of a stochastic process is just one possible outcome from a set of many possible outcomes of a stochastic process. Comma, being a random process. Now, I believe I can wipe this off, right? Okay. For instance, if there are x1, x2, and x3 random variables in a stochastic process, xt, t being member of t equals 1, 2, 3. Then one possible outcome of this stochastic process may be the sample function, or realization zero, 2, 3, for instance, full stop. Now I'm going to explain this. Please, once you finish writing that, just look up carefully. Now, you know, a stochastic process, we have said earlier on, is a random process. Am I talking to people? Now, it's a random process. And because of how random it is, there are so many possible values that the random variables that make a stochastic process can do what? Can take. Is it clear? Let's be very restrictive in the sense that we are looking at this example from the angle of being a discrete state space. Is somebody listening? Yes, sir. Now, if this is a discrete state space, such that in the stochastic process we are discussing, there are three what? There are three random variables making that stochastic process, x1, x2, and x3. Now, what we are saying, what we are calling a sample function or a sample realization is just one possible value out of so many possible values each of these random variables can do what? Assume. In this particular, this is a sample realization because there are so many sample realizations. This sample realization is telling you that this is at a time when x1 is 0, x2 is 2, and x3 is what? 3 in a discrete state space. There are so many combinations. This x1 can be 1, this x2 can be 0, this x3 can be 5. I don't know if you get me. So, because a stochastic process is a very random process where these random variables can assume so many possible values, when you take just one possible value out of so many that the random variables making the stochastic process can assume, we call that one possible value a what? A sample function or sample what? Realization of the stochastic process. Is it clear, everybody? Thank you very much. Let's go to the next what do you call it? Definition. I hope I'm not omitting anything. Okay. Are you done writing? Huh? Okay, I think we are okay with definitions. Let's now move to notation. Let's move to notation. In stochastic processes, it should be noted, that any of the following notations could be used to describe a stochastic process. Any of the following notation could be used to describe a stochastic process. One, you could use this notation x of t being member of what? Of t. Okay? You could also use this notation x of t being member of what? T. Okay? You could use this notation, that is the first one, without necessarily putting what? This. You could use the second without necessarily using what? You could use number 5. You could use this xt and t if you know what t is. Is it clear? In this case, note what I have done. I have not used the brace here. I've used what? The bracket. Is it clear? When you know what t, the indexing set, is, you could just write xt and this. You could also use this. You could also use if you know what t is. Is it clear? So any of them can be used. However, the notation xt should be avoided as one to denote a stochastic process. It should be avoided as one to do what? To denote a stochastic process. However, the notation there should be avoided as one to denote a stochastic process, since it ordinarily describes just one random variable in the stochastic process at a time t, being member of t, the indexing set. Is it clear? So you shouldn't be using this. You can use any of these and it will be acceptable. Do you know why all these are acceptable? Class, do you know why we put in the curly brace? Because we had said in the definition of a stochastic process that it is what? A collection. We had said in the definition of a stochastic process that it is what? A family. Do you remember, if you go to set theory, there was something you guys must have done called power sets. And students often make, if for example, look up everybody, look up. If I tell a student now that a set contains, there's a set A that contains 1, 2, and 3. What is the power set of A? Whether be it denoted as row A or P of A. The student will now start mentioning the power set elements. The power set elements are not elements. They are subsets. So by rule, the empty set is a member of the power set. So how many elements or subset are we expecting in the power set if the set contains 3? 2 raised to power 3, that is 8, right? Now, this is a member of the power set. If you want to write the singletons, The singletons are those unit members of the what? The power set. These are the singletons. Is it not so? I am not putting them, it will be wrong of you to put them like this when you want to list. Do you understand me? Because the rule says the members of the power set are subsets. Is it clear? So they should be treated as what? Set. So when you are describing a stochastic process, you can use any of these because in each case, you will be referring to the definition of a stochastic process, which says that a stochastic process is what? A collection of random variables or a family of random variables. You get me? So the variables are members of that collection. As such, if you use this, you are just referring to one random variable out of the collection at a particular point in time in the stochastic process. Is it clear? So this notation should be avoided. Now, let us now go to categorization of stochastic processes. Let's go to categorization of stochastic processes. Categorization of stochastic processes. Stochastic processes may be categorized into different types based on the underlying mathematical properties of such a process. Hence, one may have the following. One may have the following stochastic processes. One, based on the mathematical property of the stochastic process, you could have what is called random walks. You could have what is called what? Random walks, right? Two, another stochastic process, there are so many of them that you could have based on the mathematical property underlying the stochastic process is what is called a Bernoulli process. Yes. No, random walks. There are so many types of them. You have what do you call it? Different types of random walks. Huh? So even if you say random walk, you are not wrong. Well, W-O-R-K? No. It's random walk. Eh? That's why you would even have the drunkard walk described under it. So a stochastic process may be called a random walk based on the underlying mathematical property. Based on the underlying mathematical property, you could also have what is called a Bernoulli process. Based on the mathematical property, you could have another type of stochastic process called the Gaussian stochastic what? Process. Gaussian stochastic process. Or simply put, the Gaussian process. You could also have what is called the Wiener process. The Wiener process is a stochastic process. You could also have what is called number 5, the Brownian motion. Brownian motion process. The Brownian motion process is also a stochastic process. You could also have what is called the Poisson process or Poisson process. Huh? You could have the Poisson process. There are so many of them. Please, can I wipe this off? So, another stochastic process that stems from the mathematical property underlying the process is what we call the branching process. Number 7, the branching process. Number 8, you could also have what is called the renewal process. All these are types of processes birth process, death process. There are so many of them. Now, in general, what would you realize about the stochastic process? It is a process that is what? So random in what? In nature. Is it clear? A stochastic process, being a random process, is primarily meant to describe processes that are very, very what? Random in nature. I hope you understand me. Now, let's round up this class with applications. Let's round up this class with applications. Can I wipe this off? Let's round up this class with applications. So this will conclude our first introductory class. Our introductory class on what? On stochastic processes. Is it clear? So, my daughter left this thing open. Now, God have mercy. How do you revive this stuff? You can't revive it. She left it. You will say, "Daddy, your marker. Daddy, your marker. Daddy, your marker." Then when you now tell her, "What is which marker?" She will say, "It's my own." "It's your own. How much did you buy it?" "It's 50 rara. Everything in the house, my daughter can sell it for 50 rara. Okay, so please, I hope you all follow what is being taught. Do you follow what is being taught? Good. Now, which one? Okay, let's use this space. So let's go to applications. Let's go to applications of stochastic processes. Generally, stochastic processes is one of the best tools for modeling processes that are highly random in nature. For example, it could be used to model the movements of gaseous particles. To be used to model the movement of what? Of gaseous particles. The fluctuations of stock prices in the stock market, the growth process of bacteria in a culture, the number of patterns, the patterns of movement. Have you seen this thing when they show Premier League football? After, when they are doing analysis of Premier League football, when they will bring out one player and show the heat map of that player. Based on the heat map, they will now say, for example, I watched one on Saturday. They were trying to describe who will fit into the new coach of Man U, who will fit into the new coach system. They were now bringing out, they said that man likes playing using you would call attackers as left full backs. You understand me? Now, they were saying that somebody like Garnacho could or may not, rather, fit into the man's system, and they were using his heat map to analyze. You will see all those movements. The movement a footballer plays or moves on the pitch is so random and unpredictable for any given match. Do you understand me? So if you want to model a process that is so random, generally speaking, stochastic process is one technique in statistics that helps do what? Model very random what? Processes. Processes like how gas molecules move. Processes like how stock prices fluctuate in the stock market. Processes like how bacteria grow in a culture. Processes like how the patterns of movement of a footballer, pattern of movement of a footballer is in a certain match, etc. Therefore, one could find the applications of stochastic processes in finance, physics, ecology or biology, sports, etc. Okay? I hope you follow what I'm saying. So, under applications of stochastic process, because of what stochastic process can do, primarily class, what can a stochastic process do for you? Stochastic process will help you do what we call modeling. Is it clear? Modeling or describing processes. What kind of processes do we describe in stochastic process? Processes that are highly random in what? In nature. And because of that, once we mention, okay, for example, look up everybody. A process like studying gaseous molecules, how random they are, will be found in chemistry, will be found in physics. Is it not so? A process like studying the growth of bacteria in a culture will be found in ecology, biology, and so on. A process like studying the fluctuations of stock prices in a stock market will be found in finance. A process like, what do you call it? Patterns of movement of a certain footballer in a certain match will be called what? Will be applicable to what? Sports. If you move away from footballers, even lawn tennis, those people that they move, you see them move like this. After some time, they don't plan. No lawn tennis player will come and say, today, against this opponent, I'm going to start moving like this. Then come back, I will now move like this. Then come back, I will now move like this. Once the game starts, you see them responding to time, responding to how the game played out. And that movement is so random. Is it clear? So if you want to model the movements that is so random like that, it will be best you do it with what? Stochastic what? Processes, because it is a branch of statistics that caters to problems like that. Am I understood? Now, the last thing that rounds up our discussion for this class is this. Techniques of mathematics used in what? In stochastic processes. In order to study or model stochastic processes, the following mathematical techniques are often used or adopted. One, probability is one of them. In stochastic processes, you will need ideas from what? Probability. 2, measure theory is very important in stochastic processes. 3, linear algebra. 4, functional analysis. You have topology. 6, you have what do you call it? Vectors. 7, you have abstract algebra. 8, you have which other one? What do you call it? Mathematical analysis. Etc. All of them at some point in time can be used as a technique from mathematics to help in the study of what? Stochastic processes. So you may be dealing with a stochastic process that needs ideas from probability alone, or a combination of probability and measure theory, or a combination of probability and linear algebra. But at some point in time, for you to explain, model, or study a stochastic process, you may be using techniques from any of these mathematical fields. Okay? So that being said, if there are questions, please ask now. For those of you watching from any part of the world, thank you for joining this class. This is GER Hub, and these are my students and myself in the class STA 4101. Okay? So feel free to subscribe to the channel. If you find the content interesting, feel free to subscribe to the channel, drop a like on the video, and share the video to someone out there who wants this content. Thank you very much. Until some other time, see you.